Bismillahirrahmanirrahim. Assalamu alaikum. So now we will look at a real-world IIoT application, how a digital twin can be used for fault diagnostic and rotating machinery like a rotor. So in this case, digital twin is built using a finite element model that mirrors the physical rotor in terms of its geometry, its dynamics, and its material. So this includes even the Young's modulus and specific heat, etc. So we use different sensing technique like displacement sensors and data acquisition system to collect the vibration signals from this real rotor physical system. So these signals are the key inputs for detecting faults. On this right side here, we have the digital twin, which is continuously being updated, and it compares the measured values versus the calculated. Here, the measured and the calculated values, and then it updates the models, the parameters of the model. And until it is, and this is done after it converges. Okay, the model parameters are converged. So this sort of loop, it helps to detect the abnormal vibrations or the faults even before a fault occurs. So this is a kind of preventive maintenance powered by digital twin, powered by the IoT and simulations. So the key message is in this slide is basically the digital twin plus sensor data plus model updating. So this gives us a real time fault detection in industrial systems. And this is basically a perfect example of predictive maintenance using IIoT. Now let's discuss the platforms that support digital twin. A digital twin platform is not very different from a typical analytical platform. The main requirement is sufficient storage and computing support to store the real-time status of the assets and manage the digital twin throughout its life cycle. So in the real world, digital twins must be tuned and calibrated in the beginning, and after that, they must be kept synchronized with the physical assets. So this means periodic updates are needed so that the digital model accurately reflects what's happening in the real system. In this diagram shows the key components involved. We start from the physical asset here. Physical assets. And here, this is a wind turbine. And this wind turbine sends data to sends the sensor data to the edge device here. And that data is then processed by an asset model and forwarded to the analytical platform here, where the digital twin resides. And the cloud services enable us to make predictive periodic synchronization and between the real asset and the digital version. So so today, these days now, we have several platforms such as which are supporting the digital twin, such as the AWS Web Services, Amazon Web Services, GE Predicts, and even the Google Cloud platform which is called GCP. So these platforms offer tools that needed to collect the sensor data, run the simulation, and so let me write the features they are providing us. So they allow to collect data, sensor data especially, and even to run the simulation and update the model in near real time. Okay, so in short, the choice of the right platform is uh, the right platform. Right platform helps us to ensure that what we do is accurate, performance is oriented, and the real time functionality to achieve in the digital twin system. In this slide, we look at AWS IoT Twin Maker. And this is a powerful platform for building digital twins using Amazon Web Services. And AWS IoT Twin Maker enables the creation of digital twins by integrating diverse types of real-world data, such as like IoT data and video feeds and application data, and even the event logs to create a digital representation of uh, our physical system. And the solution works through four main steps. Uh, and these steps are, the first one is connect, and then the second one is about modeling. The third one is about compose, and the fourth one is about act. We will so in the connect here, this is where we bring data in from multiple sources. So at this stage, we bring data in from multiple sources. And AWS offers built-in connectors, or you can create your own to stream data from the IoT devices, cloud databases, and enterprise systems. This is very important. Then the second step is about the model. So in this step, we define the structure of our physical system. We define the structure. We define the structure of physical system, and we create digital representations of the components, create digital representations of our components, right? And we define how they are related to each other and how they relate to each other. Okay, from a complete digital twin graph. Then we have the compose. Here the AWS allows us to combine the 3D visual models with real-time data, with real-time operational data. And this lets us build an interactive 3D view of our physical system. And for example, such as like it is basically bring us the interactive 3D view of our plant. Okay, let me just write it down, like for plant or turbine or whatever. And then we have finally the act. This is the final using the digital twin maker plugin. We can use Grafana. We can create dashboards here, or web apps, and they can help us to visualize and interact. Okay, so we can visualize, and also we can make some interaction. Okay, interaction with our digital twin. So this enables overall uh, using this kind of digital twin. This enables many things. For example, predictive maintenance, predictive maintenance. It also help us to make like a remote monitoring, right? And another thing at some facilities, production optimization. Okay, and here are some links there where we can explore more on these this platform. Okay, now this slide highlights an important industrial application on digital twin, which is the predictive health maintenance, PHM, predictive health maintenance. And the goal of predictive health maintenance is to mainly to minimize the impact of the equipment health problems by identifying the potential faults before these cause failures. So this is achieved by continuously monitoring the equipment and equipment conditions and predicting the future issues using the digital models. So as an estimate, the annual cost of preventable maintenance issues in the industry is around $120 billion. And these are the costs that can be avoided through better monitoring and proactive maintenance strategies. And it is a continuous process as the industry evolves. So this opportunity keeps changing and continues. So when PHM strategies are implemented, they can lead to substantial operational improvements. So what are these? For example, um, in this study, Professor Don Tilbury has mentioned, for example, 3.3 times less downtime. So what does it mean? It is basically improving. This is basically improving overall productivity. And then the second thing is about 16 times fewer defects. So it is basically enhancing product quality, right? Yeah. And then the 2.4 times reduction in the lost sales. We can say this is like, and why this happens, decrease in the lost sales is basically it is due to fewer disruptions because we have managed in the above two options, disruptions and production, right? So this example taken from Professor Don Tilbury from University of Michigan. It demonstrates how digital twin technology supports the predictive maintenance by combining the real-time data with the simulation models to anticipate and prevent equipment failures. Right. So in this slide, we focus on rotating equipment. This is another or more very crucial aspect, rotating equipment. This plays a crucial role in continuous industrial process. And rotating equipment includes machines like we have pumps, motors, even compressors. And there is another thing called centrifugal systems. Okay, they appear similar to us, but they are a little different from each other. and they are all designed. They are all designed to continuously. They are all designed to continuously operate 24/7. Okay, continuously they are for years they are designed to continuously work without any interruption. And a common challenge in industry is that these machines are they take a huge amount. They take huge amount and effort to maintain them, because they have to work 24/7 and they are the key elements. Okay. Uh, so this is the common challenge, and the common challenge in industry is that these machines are frequently maintained, and basically they are maintained through run to fail strategy. But run to main strategy means that um, no maintenance is performed. This means no maintenance is performed. No maintenance is performed until a failure actually occurs. And we can say that this approach it looks what you call it looks smart. It looks good, cost effective. Looks cost effective initially, but it will lead to unexpected breakdowns, and also longer downtimes, and even the higher cost in the end. High cost in long run. Usually we go this for in short term. Okay, effective in short term, but in long term it is high cost. And here we see some common example failures. So these common example failures through this, it is like a crack. This is the bearing fault, and the surface wear and fatigue damage here. So identifying and monitoring such failure modes is essential for. This is for very important for reliable, safe, and cost-effective running of your plant. So this is here where the digital twin can play and plays a very important role in enabling the predictive maintenance. Okay, instead of reactive maintenance. Okay, so digital twin along with the basically digital twin, IIoT is a part of digital twin, or whatever you say. IoT is a part of a digital twin. So IIoT is a part of digital twin, and then it helps us to do predictive maintenance instead of reactive maintenance. Okay, good. So this slide explains the health state assessment. This is another very important. This is a key component. This is a key component of predictive maintenance. This is a key component for predictive maintenance using digital twins. And the idea is to use the real-time operational data, such as the vibration signals, to continuously assess the current health state of the machine and to predict how that state is likely to evolve over time. So this helps in identifying when a component is likely to fail long before it actually happens. So on this here we see on the left side that we see three models. we see three common models of the degradation path observed in the literature. So the first one is the linear degradation path, where wear and tear increase steadily over time. And then we have a second exponential degradation model. Here the failure accelerates rapidly. Okay, failure rapidly. In the first, we can say that the wear or tear or a fault increase steadily or linearly over time, right? The second, the exponential degradation. The third part is, we can say that this is like a hybrid model, and here the system stays healthy, okay, for some time, and then it has a linear degradation, and after that it goes for certainly exponential failure phase. So these models actually help in selecting the appropriate maintenance strategies depending on the nature of the machine's degradation. On this side, we see the real world bearing degradation example using the vibration RMS data or monitoring metrics. In all three cases, the vibration level remains relatively low during the uh, it remains low during the healthy phase, and then up to here, yeah, and then it shows a noticeable rise. You see, it is it has a rise. Sometimes it is gradual, and sometimes it is abrupt, and indicating the degradation approaching is a bit. Sometimes it is like a combination. So this approach makes digital twins highly effective for fault detection, maintenance, planning, and they help us to avoid any sort of like uh, yeah, let me write these points for. So the digital twin uh, is is highly effective for such cases of fault detection, maintenance, planning, and it can also avoid unplanned downtimes. All right. Next is this slide shows an example of degradation test using the vibration data, and we see that the graph values over time. The blue dots, these blue dots are the observations, and this red line is a threshold beyond which the equipment is considered as a risk. Okay, so here it is at risk threshold value, and this is threshold value. Threshold value. Okay, so initially we see it's healthy. We are here, so initially it is healthy, and however, as the time progresses, we observe that there is a rise in the vibration level. Okay, we observe the rise in vibration level as the time passes, and this shows the degradation. So this shows shows degradation, right? And there are multiple. Sometimes it is going plateaus, sometimes it is gradual. Like here, it is gradual. Okay, and sometimes we see the sudden jump, sudden jump. Okay, and they are all culminating towards the fault line. Okay, and here is the multi-stage health model of this behavior. The system is we see the system is starting at healthy, starting very healthy, and then it may transit into the shallow linear trend. The degradation is slow here. It means that degradation is slow and manageable. Um, if it is left unchecked, it may evolve to either the steep linear or trend or the exponential trend, and both of which will lead to the towards the failure. Okay, so eventually the machine enters the out of spec conditions. We call it out of spec condition. This term is used for machines in the field. So it will enter that, and it will requiring urgent um, requiring urgent, just let me write it. Okay, so uh, requiring urgent uh, attention. Okay, so this type of model helps engineers and data scientists to identify which stage of the degradation the equipment is currently in, and take the preemptive actions to reduce the downtime, optimize maintenance and schedule, and they can extend the life. Okay, so let me write it down also here that yeah, here. So this type of model helps engineers or data scientists, to identify the stages or the which stage of degradation the equipment is, and also this will help us to make what you call preemptive actions. This is the very valuable preemptive actions, and these preemptive actions can be, for example, the benefit is for the preemptive actions. Benefits are the benefits can be, for example, reduce downtime. Okay, this is one, and we will have like oh yeah, optimize maintenance schedule, and of course the life of the equipment will be extended. So this will extend asset life, right? Okay, So, so this slide shows how a digital twin can be used to monitor equipment health in real time and predict the remaining life of the equipment. So, from the middle graph, if we see from here in the middle graph, we see that the vibration RMS values, the data points are in the blue, and this red line is your is the fault. So initially, the system is in healthy position, and gradually it is moving towards the sub faulty line. And then if we see here the bottom graph, this is the state stage probability. So in the stage probability, we have mentioned that it is healthy or shallow linear, steep linear, or exponential. And the moment this data uh, changes its position, we will also have different probabilities here. Initially, the system is healthy, and then it transit here, and then it transit to the shallow linear degradation, and then after that it is in the exponential or steep linear degradation, yellow and purple lines. Okay, so this shows the rapid degradation in this equipment. And on top, if we see on top, we have, this is very interesting, this on the top, we see that the probabilistic we see probabilistic prediction that when the system may or the equipment may fail or fault may occur. And here we see that this thing is the probability density function, the fault probability density function, and it shows that the this is the region. If you see this, this is the region in which the possibly the fault may occur. Okay. And this red line is actually when the fault actually occurs, actual fault occur. All right. So this, let me run it. Yeah. So now you see here, we can see that it is in the healthy data stage. And now we see it is moving towards unhealthy, and as it's having some it is in this steep or exponential model area, we also see that the fault line was changing. Okay, so if we go back and then run it again, you will see that uh, the fault time PDF is initially empty initially, and as the now you see it appears. Okay, let me see. Yeah. Okay. Okay, let me run it again. Yeah. So now you will see that initially it is empty, and later on, based on the stage probability here, uh, we will start getting some of the sooner it will come. Yeah. And you see it's moving. So the vibration data is collected over time, and the model will begin transition through the degradation stage, and the fault prediction will be updated. So the fault prediction is updated accordingly as per the data. So this is the core advantage. This is the core advantage of digital twin. One of the core advantages of digital twin. Why? Because it continuously evolves. What is the point? The digital twin, it contain continuously evolves with real-time data. Right. So, in summary, to summarize this digital twin approach for predictive health monitoring of bearings, the system begins by streaming the data, real-time bearing data, and this signal may be coming from temperature, some readings, and some vibration signals. And a particle-based method is used to model the system. Multiple virtual particles are generated, and each representing a different hypothesis or trend that the system might follow, such as like a shallow or the steepest degradation. And as the data is stream in, the digital twin dynamically estimates the current health. So it is basically estimating the dynamically estimating dynamically estimating the current health of the bearing with the associated probabilities. These are important that we not only predict something, we also with the estimation we also need to calculate the probabilities. These are important things. So most importantly, prediction, by the way, prediction has no meaning, in fact, if you don't have the proper probabilities along with that. Uh, so so most importantly, it predicts the fall time, and giving not just a single estimate, but it gives us the confidence of interval, which is crucial. So what it is estimating is it is estimating the health stage, the predicted fall time, probability of each health stage, and also the probability density function of the expected fall time. So this comprehensive view supports the condition-based monitoring. And again, the same thing minimizes the downtime and avoids the unexpected failures. Now, this we will do this example. Okay, so in this example, it highlights how digital twin, edge computing, and cloud-based machine learning can be integrated integrated to enable online anomaly detection in the automation systems. So with the advancements of the sensor technologies and large volume of data can be now collected directly from the field, and edge computing allows us this data to be processed and stored locally at the edge of the network near the physical systems. The benefit is this reduces latency, improves response time, and enhances the data privacy. Meanwhile, the cloud computing offers flexibility to process more complex analytics and storage using centralized infrastructure. And this combination supports a distributed yet coordinated system. So just like the cyber physical system, this architecture has three core components. And these three core components include physical entity such as machine, virtual model. This is like a digital twin, and the interconnection that synchronizes both. So the proposed framework, which is we are using this cited work, is it fuses the real-time data from the physical system with the edge computing to capture accurate information. This is then used to run analytics, Anomaly detection models, it leverages both the digital twin and the cloud-based information or intelligence. So this system allows us for continuous monitoring, timely fault detection, and smarter decision making in the automation system. Okay. So, right. So in this slide, we explore a framework for anomaly detection using the digital twin technology. The framework includes a physical entity like a machine or a system, and its digital twin. The digital twin is basically in two layers. The one is the edge layer and the other is the cloud layer. So let's see in the what we have in the edge layer. In this layer, this is positioned near to the physical system, and it serves like two major functions. Number one is the data processing, and the such as it structuralizes data cleaning and feature extraction, and this also reduces the load on the cloud infrastructure and it minimizes the network delays. Secondly, it runs a model locally. So this enables the real time analysis and for quick response at the source, near the source of the data. So, for example, this may be a production machine or some sensors. And then we have the cloud layer. This layer, it takes over more computationally heavy tasks, and it supports model generation, model updating, simulation, data analytics, visualization, and process planning. So this layer also provides like cloud storage for managing large volumes of incoming data from the edge. This architecture basically supports the communication through various industry protocols. So we have MT Connect, OPC UA, Wi-Fi, Zigbee, Bluetooth, Ethernet, so that this network allows us to connect with different like robots, conveyors, PLCs, or other controllers. So in this in summary, this framework ensures that the critical anomaly detection tasks are performed locally for speed, while the complex tasks can be shifted here on the for the complex analysis on the cloud for model updating and handling things in the cloud. Right. Okay, now in this slide, we have a workflow for anomaly detection. It has steps: step 1, 2, 3, 4, 5. Here we will go through each step one by one. The first step is the digital twin modeling. This step involves creating a digital replica or shadow of a physical entity, and it has three key components. The first one is the geometric model, which mirrors the structure of the physical entity within the cyber world, usually a cloud layer. Then we have the second, a functional model, which describes the system's behavior and functional logic. And then we have the information model, which enables the connectivity and interactions between a physical entity and its digital twin in the edge layer. At the step 2, we have data acquisition and pre-processing. Here, actually, the real-time data are collected from the equipment using the controllers, sensors, smart sensors, and data acquisition devices. And then the data is further filtered, cleaned, and structured to make them suitable for model training and diagnostic. In this step 3, this is detection model generation and updating. In this step, the pre-processed data are sent to the cloud layer where the machine learning or analytical models are created and updated regularly. So these models help identify anomalies and detect the patterns that may indicate early signs of system faults, as we discussed before. Okay, so this is the fourth step about detection. In this step, the detection model is generated in the cloud layer and is now in this step the detection model which is generated in the cloud layer is now deployed on the edge layer, and this enables the real-time anomaly detection close to the physical system. and the predictions are continuously monitored and logged in by the edge. So by comparing the real world operational data with predicted values, we can verify the accuracy of detection model. And if repeated discrepancies are observed, it may signal that the detection model requires the retraining or updating. And then we have the fifth step about maintenance strategy generation. So based on the anomaly detection results, the system generates a maintenance strategy in the edge layer, and this ensures that any detected faults or degradation trends are addressed promptly. So the strategy is then communicated back to the physical system, allowing the system to take preventive or corrective actions or maintenance actions in the real time. So this is like a closed loop workflow from modeling to maintenance, and it demonstrates how the digital technology can support the uh, the the intelligence or autonomous monitoring and decision making in their industrial systems. Okay, so in this slide we have data processing. These are the key stages involved in data processing for updating the anomaly detection models using digital twins. We start with data preparation, and at the at the edge layer, the raw data collected from the sensor must be cleaned and processed to ensure it is suitable for further analysis. And this includes and ensures that we do the data cleaning, integration, reduction, and transformation. The At this stage, the next stage is about the model generation, and at this stage we can use various AI and machine learning algorithms. They can be applied for anomaly detection, and since the training models with the large data sets is computationally expensive, so the cloud is typically used to accelerate this um, step. And once the model is trained, it is deployed to the edge layer for detection. So this enables real-time or near real-time anomaly monitoring and detection close to the physical system. Finally, we have this model updating. As the system evolves, the model must be synchronized with the latest operational conditions. So this is achieved through continual learning, where new data is used to automatically retain the model. And this in this diagram, we see that the complete pipeline of the from raw data to pre-processing to the feature extraction um, stages, and model training and evaluation and deployment on the edge. So, and also utilizing the new data. Okay. Okay, finally, we are on the last slide of our course. So this final slide represents a real-world prototype implementation of a digital twin developed for an absorption chiller. Uh, Focusing on the anomaly detection, the system architecture is divided into three layers: the physical layer, edge layer, and the cloud layer. At the physical layer, uh, we we have the physical asset, the Libre absorption chiller. It is equipped with the sensors, and the sensors collect data in real time about the equipment conditions and performance. And the edge layer, this data from the sensor is sent via network to, they have used a Raspberry Pi 3. This serves like edge device. And at this level, the data undergoes like pre-processing or local storage, or the edge device also runs lightweight predictive models to perform initial health assessment close to the physical system. This is what they have done. And then comes the cloud layer. All the data, all the process data and insights are transmitted via the through the Wi-Fi to Xilinx cloud, where more computationally intensive tasks are performed. So these may include these basically include identifying the key factors storing large scale data, training more complex models, maintaining the digital twin interfaces. So this three-layered approach demonstrates how digital twins can be implemented effectively using the edge and cloud integration to support like smart maintenance and fault prediction in industrial HVAC systems. So, with few final words, that uh, we have wrapped up our journey into the digital twin for anomaly detection and maintenance, and we have looked at the practical cases. So I hope you enjoyed the material, and I hope and wish that this should be useful for you. Thank you very much. This ends our lecture and the course as well. Assalamu alaikum.